So I'll cover a few different aspects, some general introductory comments about the nuclear landscape, a little bit of isomer history, the different types of isomers, isomers far from stability, and then attempts to manipulate isomers in terms of using their energy storage. The nuclear chart is, I'm sure, very familiar to you, and there's something like 3,000 observed nuclides, but every one of those has the potential to have long-lived excited states, and every nuclide has extra dimensions than just seen in the nuclear chart in terms of energy and angular momentum. And there can be the formation of pockets in the potential energy surface that will form long-lived states. The history of isomers really began with Surrey. He realized, or he hypothesized, that you could have different states of a given nuclide. He said they could be different in their stability, meaning a different half-life and different modes of breaking up. So you could have one state that gamma decayed and another state that beta decayed, for example. It's not entirely clear how he came to that view, but it was a good suggestion. And a few years later, Otto Hahn found some evidence for an isomer in protactinium-234, although it was called a different thing at the time. And he was looking at the decay series of uranium-238. And he realized that he was making two different states of the same nucleus with different half-lives. And they both beta decayed. And although he couldn't really prove his case at the time, he did make the statement that such a case has not been observed before in radioactive decay. And he turned out to be quite right about that. But it was not accepted at the time because it was a one-off. And some years later, von Weizsäcker of the semi-empirical mass formula fame, when he was only 24, he hypothesized that isomers could be formed due to angular momentum changes, and there could be large differences in angular momentum between the initial and final state. And I've put the angular momenta as now believed, or for protactinium-234, and the isomer itself is a low spin state, spin 0, whereas the ground state is spin 4, and a change of 4 units of angular momentum is quite a lot in terms of emitting radiations. So that accounts for the half-life of the isomer, although it's fascinating that this particular case is still not fully solved from a nuclear structure point of view. With the last paper I found published about the isomer in 2016, where they observed for the first time the direct photon emission from the isomer, which was, well, the direct electromagnetic decay, I think would be more precise, of the isomer, which was 2.5 keV only. So there's still things to learn about the first ever isomer, but I can't dwell on that too much. But I would like to draw your attention to this wide time gap between the first isomer observation and the explanation. And in the meantime, there was lots of progress in nuclear physics, just not a lot of progress with isomers. And one of the key areas was in conversion electrons. And these turn out to be important for isomers because the electromagnetic decay of an isomer can be by gamma ray emission or conversion electron emission, and they compete in very different ways depending on the angular momentum changes. This got mixed up with beta decay, and there's a long story, and so I'm just showing on the screen here the cover of a book devoted to the different findings primarily of Lise Meitner in Berlin and Charles Ellis in Cambridge, working respectively with Hahn and Rutherford. But one of the fascinating aspects about conversion electrons is that they showed the discrete nature of the electron emissions from the nucleus. And this was really the best early evidence for quantization of nuclear excited states. And the idea of quantized excitations was still very new, and it's hardly surprising that isomers were hard to understand when the quantum nature of matter was still not understood. But that was a developing area. So here's the aspect of conversion electrons that shows how they can dominate the decay process, so that the nucleus gives its energy to an atomic electron, which is then ejected, and the ratio of intensities of electron to gamma ray emission showing on the right here. This is a theoretical calculation, but it's pretty well understood now, and that you can see these ratios of electron to gamma ray emission go up to values of here 10 to the 10. So it's essentially all the decay for low energies and high multipolarities is by electron emission. And there may be a moral there, because this conversion electron emission is one of the key and common aspects of the nucleus interacting with its atomic environment. And this may be a route to controlling nuclear excitations with some external fields. Just as an experimental demonstration of the importance of electron conversion, I show this picture of a storage ring at GSI in Germany, and the half-life of an isomer, which in the neutral atom was just half a second, but in the storage ring, with all its electrons, all its atomic electrons removed, the conversion electron emission was eliminated, and the half-life increased by a factor of 30. So with all the electrons removed, it does emit gamma rays, but it's very different behavior to the neutral atom. In terms of the naming of isomers, the name came from chemistry, where chemical isomers refer to different arrangements of atoms. So in the same vein of that language, the nuclear isomers refer to different arrangements of the different nucleons, given set of nucleons. But it's every nuclear excited state can be said to be a different physical arrangement of a given set of nucleons. And so isomers are also associated with measurable half-lives. And this is still not defined, but it approximately means more than a nanosecond. So that doesn't sound very long, but it's still a long time compared to typical nuclear excited states. And then just to connect with atoms, in the same way of the quantization of states and their angular momenta being important for nuclear isomers, they're also important for electronic metastable states. They don't use the term isomer, but for high angular momentum transitions in atomic excitations, there are also some very long half-lives. It's just they're not typically observed because the atom, if it's in some apparatus on the Earth, the atom interacts with its environment and loses its energy by collisions. But metastable atomic states are very important in stellar atmospheres and such like. Just a brief view over extreme isomers. The longest lived isomer, Tantalum 180, has a half-life of much more than the age of the universe. And this is the only example of such a long half-life. So it's the only isomer that you can dig out of the ground. You can mine Tantalum 180, albeit rather mixed up with Tantalum 181. And you can make a target of Tantalum 180, which we'll come back to. There's some isomers with high spin and high energy up or above 10 MeV, which are technically unbound to both proton and neutron emission. But so far, these high-lying isomers are not observed to emit protons and neutrons, and this has everything to do with angular momentum, well, the angular momentum barrier, I suppose, is the simplest way of saying it. The lowest energy isomer is of great interest these days. Its energy has been pinned down to just 8.2 electron volts, and its half-life is 7 microseconds in a neutral atom, but in a particular lattice just very recently, there's, I think it's a paper on the archive at the moment, in a particular lattice, the half-life extends to 10 minutes by blocking the conversion electron emission. So there's this has been particularly trumpeted as a possible starting point for a nuclear clock, which would be much more accurate than an atomic clock. And then there's low and high mass examples, which I won't discuss anymore just at the moment. I just emphasize again that the isomers can decay by gamma ray and conversion electron emission, and ground states cannot decay in such a way. So if you want to manipulate nuclear states with electromagnetic fields, then isomers are a good place to start. It's easier to manipulate isomers than all the other excited states because they have long half-lives. That gives a chance to see the effects of the manipulation, hopefully. There are a lot of isomers, and according to the most recent compilation just published in Atomic Data and Nuclear Data Tables, there's some 2,600 of them with half-lives greater than 10 nanoseconds. And it's important to notice that the distribution of isomers along with different mass number is clearly not random. And this is seen more clearly if you spread it out a bit and look at the nuclear chart, both proton and neutron number. And you can see a clustering of, now this is just a somewhat arbitrary decision to look at the distribution of isomers with an energy of more than an MeV and a half-life of more than a millisecond. But it shows clearly a clustering of the isomers close to closed shells and then occurrence well away from closed shells. And this reflects the two main different types of isomers. There's the spherical, what we might call shell model isomers, close to closed shells, and the deformed isomers where there's an axis of symmetry, and one can specify the K quantum number as the projection on that axis of symmetry And that gives an understanding of the majority of these cases that are well away from the closed shells. But we can recognize several different types of isomers, more than 3, depending on how you like to subdivide. But I'll just say really that there's spin isomers account for the majority of the type that von Weizsäcker explained in 1936. Then the deformed nuclei contain K isomers, and this was understood by Alliger and co-workers in 1955. And then there's also some shape isomers where the inhibition is not due to angular momentum, as in the first 2 kinds, but in the change of shape of the nucleus. And this was first recognized by Polikhanov and co-workers in 1962 in connection with fission, because there were states observed that fissioned with extended half-lives. So level schemes that correspond to these 3 different types are shown here, and they're just examples as simplified level schemes too, and the half-lives, but you can't really tell what kind of isomer it is from the half-life, and you can't see directly how you can't really quantify the inhibition of the electromagnetic decay. But if you compare with the so-called Weisskopf single particle units, which are admittedly very simplified visions of proton radiation strengths, it's nevertheless a very convenient rule of thumb. And you can compare the Weisskopf rates with the observed rates. So here, in this spin isomer, this is forced to decay by at least E4 radiation, because all the states below it are of much lower angular momentum. But if you work out the Weisskopf hindrance factor, it's about unity. So spin isomers are characterized by radiation strengths of very approximately 1 Weisskopf unit, whereas K isomers, you find that the Weisskopf units are very inhibited. So these are the Weisskopf hindrance factors of 10 to the 9 and 10 to the 13. So the transition strengths are vastly reduced, not just by the high angular momentum, in this case E3, but also by something else. Even this E3 is inhibited by 10 to the 9, and that's the K quantum number. So I'll say a little bit more about that in a moment. And then the shape isomer, the inhibition, about 10 million inhibition, is from the change of shape from super deformed to normal deformed. And this is an example of a fission isomer. So part of the decay is through fission and part is through electromagnetic emission. I'll just say a little bit more about K isomers. So here's a depiction of the prolate-shaped nucleus, which has an axis of symmetry, and the projection of the angular momentum on the symmetry axis is conserved and called K. And it's possible to define a degree of forbiddenness, which is the change in K minus the angular momentum of the radiation. This E1 decay of the 8- isomer in hafnium-178, the change in K is 8 units, and it's called 7-fold K forbidden. And if you take the 7th root of the Weisskopf hindrance factor, you get a number which is 79 for that decay. If we do it for the decay of the 16+ 31-year isomer, then we get a number 66, which is similar to 79. So this so-called reduced hindrance boils down the inhibitions in a way that's easier to compare. And very roughly, these so-called reduced hindrances change from 10 to 100. That's a very approximate range. But it's more manageable than these inhibitions compared to the Weisskopf estimate of more than 10 to the 10. So this hafnium-178 isomer is extremely famous because it's up at 2.5 MeV, and yet it lives for 31 years. And it's even lived long enough to be able to make it with an accelerator and separate it out. And the people in Paris were very good at working on this. And there was some work with the Paris separator at the CSNSM, which using lasers, which identified the hyperfine structure of the 31-year isomer after separating out the isomer and making a beam of hafnium-178. And this is a famous result because it's still not properly understood. And it was augmented by Bissell and co-workers at Uvascular, who identified, made some, using the Igisol separator, made a beam of the M1 isomer. And if you compare the mean square charge radius from the laser measurements of the isomers and the ground state, you can see that particularly the 31-year isomer is really substantially smaller. Its mean square charge radius is much less than the ground state, and yet the quadrupole moment, which is measured at the same time, is very slightly more than the ground state. So it hasn't actually got smaller in terms of its charge distribution, but its mean square charge radius has gone down. So this can be discussed qualitatively in terms of skin effects and the effect of pairing to sharpen up the surface, but it remains somewhat enigmatic, and it illustrates how if you can make beams of isomers, you can do rather fascinating measurements that are different from what you get with ground states. I'm going to be looking more at exotic nuclei, that is nuclei far from the valley of beta stability, and some structure issues to do with them, and discovery issues. So the exotic isomers, meaning isomers in exotic nuclei or isomers nuclei, need some special techniques. But in fact, there are quite a large number of techniques that one can use to discover new isomers. And here's a bit of a menagerie, rather a lot of different pictures, but the background is quite simple. So number one refers to gamma decay, and this is just an example of a gamma ray spectrum coming from an isomer measured at RECON, happened to be in 2020. And measuring isomeric gamma decay is still the most prolific way of finding new isomers. But there are many other decays of isomers, types of decay, and I just thought it was of some interest to show these different types. So here's conversion electron emission of gold 205. This was measured at GSI, and these are conversion electron peaks. So this is the K electrons and the LM slightly smaller peak. And that it comes with an associated half-life of 6 seconds. Then number 3 here is an illustration of alpha decay. So the isomer, there are isomers in dysprosium 270, sorry, Darmstadtium 270 were measured from their alpha decay. And then number 4, here's proton decay. This was the first example of proton decay from an isomer, which was measured before ground state proton emission in cobalt 53. And then number 5 represents fission decay. Nobelium 250 has an isomer which lives 10 times as long as its ground state. And this is a 40 microsecond isomer compared to a 10 microsecond ground state. And that itself is the subject of ongoing interest in the extent to which isomers can confer extra stability. And then number 6 is laser measurements. So the laser measurements I showed of hafnium 178 were not finding a new isomer, but here in gallium 50, an isomer was identified from the laser hyperfine structure. There had to be an additional state, and it wasn't necessary to measure its decay, wasn't necessary to measure its half-life. You could just tell from the spectrum that there was a ground state and an isomer. And then number 7 in this list is mass measurements. And mass measurements come in various types. And here I just illustrate 2 of them. There's the Penning trap, which is a very small device, a few centimeters across, which has been used to discover new isomers. And again, you don't need to measure the decay. You just find a split structure in the resonant signal. And similarly, in the storage ring, but now a very massive device, the circumference of 108 meters, isomers can be detected without needing their decay. And this illustrates one atom that does decay. And one of the remarkable things about storage rings is they can detect single ions as a function of time. So here there's a single ion of tantalum 187 in an isomeric state. And as time progresses, it continues to circulate, and then suddenly it decays, and it must be gamma decay to its ground state. And the ground state can be measured in separate measurements. And there's a reference here of the ground states of tungsten 187 and rhenium 187. And we know this must be gamma decay because, well, for a start, there aren't any conversion electrons. It's 73 plus, so it's fully stripped of its electrons. Even if there was an electron, this wouldn't be electron conversion because that would change its charge state. So it would go to a completely different orbit in the ring. And by measuring not just one ion, but measuring, in this case, 17 of them, quite a good accuracy was obtained for the centroids of the trajectories, such that the energy of the isomer could be determined to be 1789 plus or minus 13 keV. So this is without knowing anything about its angular momentum. It's just discovering there's a energy state of a couple of MeV. And this was from 2010. And this set a challenge really to measure the spectroscopy of this isomeric decay. And in the storage ring, the beam was gold 197, and it fragmented on a beryllium target and made many different nuclides in this mass region, which were separated in the storage ring. And the orange circles represent new isomers that were found using this technique. all in one experiment. And this red ring was Tantalum 187, which was the specific example that I showed. Now, there are other ways you can get to Tantalum 187 other than gold fragmentation. And in particular, tungsten 186 is stable, and you can hit it with a heavy ion beam and look for the products through multinucleon transfer. Now, studying these elements is quite problematical if you want to look for longish half-lives and separate out the different masses and isomers. These are so-called refractory elements, which have very low vapor pressures, even at very high temperatures, and they're particularly difficult with isotope separators. But at the same time as some of these measurements were going on, the group at Riken in Tokyo were developing something they called KISS, which is the KEK isotope separator system. And that uses a gas at high pressure to stop the recoiling ions from the xenon multinucleon transfer, and in this case with a tungsten target. Now, it's no mean feat to extract refractory elements, because if you let them stop in a foil, which is a typical situation in an isotope separator, then they stay in the foil. But in this case, they never get to a foil, they stop in the gas, and then when they come out of a little exit hole, they are resonantly ionized with lasers. So the ionization scheme needs to be established beforehand, and then the element can be selected at this point, and the mass in a standard dipole magnet. And so you get both mass and element selection to study with beta and gamma ray spectroscopy. This was really the first time an isotope separator type of system has given access to neutron-rich refractory elements. And so we tried this to look for Tantalum 187, and this worked extremely well. So here's a gamma ray spectrum. This is gamma ray coincidences summed up, and there are a whole lot of gamma rays coming from the isomer that had been first identified in the storage ring at GSI 10 years previously, and the excitation energy matched pretty well. So the storage ring measurement was 1789 plus or minus 13, and now the gamma ray spectroscopy gives 1778 plus or minus 1. And it also gives the whole series of gamma rays that come out as seen in the gamma ray spectrum. And these can be studied to learn about the structure as seen in the isomeric decay. And in this case, there's a rotational band that's of particular interest because it's not quite regular. There's some, like say, staggering of the two different signatures of the band, or if you plot the energy difference divided by the spin, you get this oscillation effect, which is characteristic of, well, I would say, of some band mixing, usually induced by mixing of the K quantum number, but it can be due to triaxiality as well. And the triaxiality aspect is particularly relevant here because this is a region of the nuclear chart where there's a transition from prolate shape to oblate shape. And this transition should be rather sudden in the tantalum. And this seems to show that the transition hasn't yet arrived, but it's getting close from these oscillations, which can be compared with the different tantalum isotopes and the different rhenium isotones. But that's too much detail to sort out with you at the moment. But I just point out that there is this oscillation which implies some band perturbation, and at the same time we can extract the reduced hindrance value, which seems to be consistent with this. It's in the range 10 to 100, as I mentioned before, but it's on the low side, which has probably got something to do with the perturbations in the band that it's decaying to. So there's a lot that can be extracted from this kind of information. But I wanted to spend a bit of time talking about applications of isomers beyond nuclear physics, and two ways that isomers are very heavily used, which I won't go into in more detail than is on this slide. One is medical imaging with technetium-99, and that's an isomer, and that's quite an ideal situation because chemically, the technetium gets into different parts of the body depending on how it's introduced, but it can be used to show up joints that have problems. But from a radiation point of view, the isomeric decay involves 141 keV gamma ray, and this is a very convenient energy for detection with gamma ray detectors, and it's become very popular. But the downside is that there's a worldwide shortage of technetium, and it's quite a problem to keep up the supply in an economical manner. But that's really a different story. Another very common use of isomers is iron 57 metastable state is used in Mossbauer spectroscopy, and that's a whole field of study in itself. But the fact that it's an isomer is significant because it gives a very narrow line width, which gives very precise information of various chemical properties. But to go to less well-established aspects of isomer applications, it would be very desirable if the decay of a long-lived isomer could be speeded up and the energy extracted. So with conversion electrons, if you remove the conversion electrons, then the isomer decay slows down because it can't use the conversion electrons. But there may be other ways by electromagnetic excitation from an isomer to an intermediate state and then release the energy. So this has been a wish to be able to use external radiation to manipulate nuclear energy. This has been a wish for many years. Is it getting any closer? Well, perhaps. Just to in a rather simplified way, to clarify that the energy, where it fits in terms of the amount of energy, nuclear fission is roughly 100 MeV per nucleus that fissions. Nuclear isomers can carry roughly 1 MeV, not 100. And chemical energies are more like 1 electron volt. So compared to chemical energies, isomer energies are pretty huge, and there appears to be potential there to develop devices, one might say, batteries perhaps. And this shows an example, perhaps the best example of de-exciting an isomer with external applied radiation. In this case, it's the Tantrum 180 isomer, which is the longest lived, only quasi-stable isomer. And that was irradiated with bremsstrahlung photons by Belich and colleagues. And they found resonances at, these are the lowest energy resonances they found for the de-excitation of the isomer through the ground state of tantalum 180, which is only 8-hour half-life. My involvement was only to point out that these resonances match up with excited states that had been established from gamma ray spectroscopy of tantalum 180. And it can be seen that these also, these can be E1 transitions going from 9- to 8+, 9- to 9+, 9- to 10+. So there's a natural understanding of these resonance energies. And so that they go through specific quantum states and decay back to the ground state. There's a lot one can learn from this in terms of the K quantum number. And Belich and co-workers were really interested in how tantalum 180 survives in stellar environments, because if this photon irradiation can destroy it and then through the ground state, it's quite surprising that there's any tantalum 180 existing on the Earth at all. It is very rare, but it does exist. So there's other stories there to do with isomers and astrophysics. But on the trying to extract energy out of isomers by photon manipulation, it doesn't look too good really, because you're using 1 MeV and you get out just a little bit. So it shows the principle that it does work, but can low energy photons be used to de-excite isomers? That's the next question. Once you feel comfortable that photons can be used, can low energy photons be used, much less than an MeV? And this has been the subject of, unfortunately, quite a lot of, what's the right word? What's the right way of saying it? Disappointing results, especially associated with the hafnium-178 31-year isomer. But this was irradiated with roughly 100 keV X-rays. And the idea was that there should be some K-mixing level, intermediate level, that could funnel the excitation back back to the ground state and release the 2.5 MeV as the isomer. Well, there's been a few articles written about this. The first one, I guess the most famous, was Collins and co-workers in 1999 published a phys rev letter. And this led to a lot of discussion and more papers, mainly negative results, although Collins and co-workers continued to produce papers showing positive effects. It appeared to be somewhat closed off by a former student of Collins, Carroll, who published a paper in 2009 using synchrotron radiation from Spring 8 in Japan, and showed no significant isomer. But nevertheless, there's a Ukrainian group, Kuryshuk and co-workers, who more recently have claimed that there is indeed an effect. So the book is not closed on this, but it's pretty hard to do the measurement, because it seems to be small effects in the presence of the activity of the 31-year isomer. But if you're an optimist, there's still something to find here. But the problem from a nuclear structure point of view is this K mixing level has never been identified, and it should be within the range of gamma ray spectroscopy. That there should be some level that would take the flux when it's irradiated with X-rays. A case, so that encourages us to look for a case where the intermediate state, in that case a K-mixing level, really is already known. But we go to spin isomers rather than K isomers. And I just remind you here, internal conversion we discussed before, that there's the inverse of internal conversion, which is referred to as NEAC, or nuclear excitation by electron capture. And here the electron comes in from the outside. There needs to be a vacancy on an inner shell, and this can excite the nucleus. And maybe this is more productive than shining photons on the nucleus. And the particular case which seems to be very promising is molybdenum-93. And Gosselin published a couple of papers looking at the effects of molybdenum-93 in a high-density plasma at elevated temperature, theoretical work. And they predicted that the half-life should be reduced by a factor of about 1 million in the right kind of plasma conditions. So going from 7 hours down to 30 milliseconds. So that seems to be very encouraging, that it should be possible to manipulate isomers in a plasma, but what's difficult is to introduce isomers into a plasma in a way where you can make these kind of measurements. So other people, it shows the intermediate state and the excitation pathway that is needed. Other people have tried to do this with a beam-based experiment. In particular, Chiara and co-workers published a Nature paper in 2018, claiming to have pinned down this pathway using a beam of molybdenum-93 cascading down through the isomer, excited up, and then going down to the ground state. And they published some quite interesting gamma ray coincidence spectra, one of which is shown here, which seem to show this, this 268 keV gamma ray is the one that shows it's gone up through this pathway. But it seemed too good to be true, and perhaps it was. It was resulted with a barrage of criticism. So 3 PRLs, 2 of them theoretical, and finally another experimental measurement, which suggested that this interpretation of the gamma sphere data by Chiara et al. Couldn't have been right. But this is another case where the book is still open, and it's too early to write it off, in my opinion. But it's hard to see how you can overcome gain a factor of 10 to the 9, but that's awaiting further data from Chiara and company. I think they're trying. And there are other examples of this NEAC process that could be tried. For example, antimony 129, there could be a 10 keV excitation, and it should be possible to do a storage ring experiment where all the electrons are stripped off, and then when the nucleus stops in a foil, having been cooled down in this suggestion using cry-ring at GSI, then all the capturing of all the electrons may be able to excite this pathway and de-excite the isomer. So that's using the atomic electrons, but there are other processes for isomanipulation. I don't have a lot of time, but I will mention them very briefly. Another electron process is called nuclear excitation by electron transition, uses an inner shell electron falls into a vacancy and excites the nucleus. And this has actually been shown in a way that appears to be totally reproducible, although quite a small effect in gold 197. And this has been very helpful for establishing the scale, the experimental strength of the process to compare with calculations. And Kishimoto has gone on to several more measurements after the discovery in 2000. But rather different is the possibility of making a Bose-Einstein condensate of isomeric atoms. And this is a little bit hard to conceptualize, but with the group 1 metals like sodium, lithium, cesium, rubidium, you can make Bose-Einstein condensates at about 100 nanokelvin. So there you get a whole collection of atoms in a single quantum state. And it's an extremely low energy phenomenon. But if those atoms happen to be in isomeric states, then there's the question is what would happen? Because the atoms are in the lowest energy state. It's a single quantum state. And it's hypothesized that the isomer decay would become a collective phenomenon. So there would be a sudden burst of coherent isomer radiation when one isomer triggers it. But this, I'm not sure how many people think this is really going to happen, but nobody has put isomers in a Bose-Einstein condensate before. And there are attempts to do this underway at Jyväskylä at the moment. Then finally, isomer pumping with synchrotron radiation has shown some notable successes. I can't spend the time on it that I'd like to, but just note thorium-229, we've mentioned before, published in Nature. Iron-57, we've mentioned before, published in Science. Iron-57 again, published in Nature. So these are significant advances in the manipulation of isomers using synchrotron radiation. And I think we can expect further advances. And really finally, the using lasers rather than synchrotron, using lasers to do the excitation. There was a breakthrough here by Feng and co-workers in China, in Shanghai, using their laser facility. And they demonstrated that you could excite krypton-83, a 1.83 hour isomer via a higher excited state. It seems to give some very interesting possibilities, but time is running out. I'll just remind you, Marie Curie said many things, but one of them was, one never notices what has been done, one can only see what remains to be done. And that's, we have to keep a focus on the future to learn from the past. So in summary, I would say that isomers were discovered 100 years ago. They're key states in the study of exotic nuclei, and they can store large amounts of energy. Perhaps here, if it is that isomer manipulation is an emerging field of research, that's just an opinion, but it's not on the dead end. And the key to this manipulation lies at the atomic nuclear interface. So thank you for listening, and I hope you you'll feel free to ask any questions.